For decades, we thought we knew the birth story of the universe. There was a simple rule: the first billion years were a chaotic nursery where baby galaxies formed. But we were wrong, terribly wrong, when the James Webb Telescope peered into the dawn of time. It didn't find kindergarteners, it found monsters, and because of this, everything changed. A fully formed galaxy, appearing just 290 million years later. This should not have happened. Galaxies growing as large as the Milky Way in 500 million years. Physics would not allow it. Black holes growing 25 times faster than the theoretical speed. This was impossible. But the truly shocking part wasn't the existence of these structures. It was just how wrong our models were. This situation calls the fundamental laws of physics into question. If this cosmic crisis is blowing your mind too, then like the video and subscribe, because the universe as we know it has come to an end. Are you ready? Let's begin. For years, we thought we understood the size of this planet we walk on, the seemingly endless blue line we see when we look to the horizon, the hours-long flights crossing oceans and continents so large they are hard to trace even on a map, all gave us the feeling that the Earth was a colossal place. We felt this sensation down to our bones, because our biological evolution encoded this surrounding scale as large. This intuitive sense of bigness is the first illusion we must destroy. Because the moment you begin to compare Earth to its neighbors in space, you are confronted with an extremely uncomfortable truth. This planet, must know, the one you stand on, the one that holds all our history, our wars, and our civilizations, begins to shrink, and this shrinking never stops. First, let's start with numbers we can physically touch and feel. The Earth's circumference at the equator is a measured and verified figure of approximately 40,075 kilometers. This might seem like just a number to you, but let's turn it into a physical experience. If you boarded a commercial aircraft traveling at about 885 kilometers per hour, and flew in a straight line without stopping or refueling, it would take you more than 45 hours to return to your starting point. That means being suspended in the air for almost 2 full days. But therefore, if you attempted the same journey in a car at 110 kilometers per hour on an imaginary highway over the oceans, driving without sleep or breaks, it would take you a full 14.5 days. For 2 weeks, you would have to drive non-stop, just to trace the outline of the planet you were born on. This is the Earth at a human scale. But when we shift the perspective slightly, this giant sphere suddenly becomes incredibly delicate. The deepest wound on our planet, the Mariana Trench, plunges about 11 kilometers below the surface in the western Pacific Ocean. It is so deep, the pressure reaches 1,000 times that of sea level and could crush a nuclear submarine like an aluminum can. But here is the brutal ratio that reframes everything. The Earth's diameter is about 12,742 kilometers, the deepest point on the planet. The Mariana Trench is just an 11-kilometer scratch on this massive sphere. If you were to shrink the Earth to the size of a standard basketball, it would be impossible to feel the Mariana Trench with your finger. You would run your hand over the ball, and that immense depth, that terrifying high-pressure chasm, would feel perfectly smooth. Because what is unreachable for a human is a rounding error for the planet. This is the first lesson of cosmic scale. The things you believe to be enormous become immeasurably small when you take just one step back. Now, let's turn our gaze upward to our source of life. Earth orbits the Sun at an average distance of 150 million kilometers. Astronomers call this distance one astronomical unit. But to make sense of this distance, let's get back on that plane. If you tried to fly to the Sun, the journey would take 19 years. A child born on the day of departure would be old enough for college by the time you arrived. Even light, the fastest thing in the universe, traveling at 300,000 kilometers per second, takes 8 minutes and 20 seconds to reach your eyes from the Sun. So, when you look at the sky right now, you're not seeing the Sun. You're seeing what it looked like 8 minutes ago. If the Sun were to disappear this second, you would have to wait the time it takes to make a coffee to even notice. But distance is only half the story. What is truly shocking is the size of the Sun itself. The Sun's diameter is about 1.4 million kilometers. For comparison, you would need to line up 109 Earths side by side to reach from one end of the Sun to the other. In terms of volume, the situation is even more devastating. Because a full 1.3 million Earths could fit inside the Sun, not side by side. Inside, all the oceans, all the continents, all the cities, copied 1.3 million times. The Sun would swallow them all, and still have room to spare. This yellow dwarf star, alone, accounts for 99.86% of the mass of the solar system. All the rest, Jupiter, Saturn, all the planets, all the asteroids, and us, we are just sharing the remaining 0.14% of crumbs. Even Jupiter, which can fit 1,300 Earths inside it, is a footnote next to the Sun. The Earth is not even a footnote. It is a cosmic dust mote, orbiting a thermonuclear furnace that converts 4 million tons of mass into pure energy every second. This feeling of smallness you're experiencing is just the surface of the truth, because the defining feature of the solar system isn't its size, but its terrifying emptiness. The distances between planets make the human concept of far completely meaningless. Neptune is located about 4.5 billion kilometers from the Sun. When a beam of light leaves the Sun, it takes over 4 hours to reach Neptune, sending a radio signal there. Even at the speed of light, takes hours. To visualize this emptiness in your mind, let's build a model. Let's shrink the Sun to the size of a grapefruit, about 20 centimeters. On this scale, Earth would be a pebble, less than a centimeter wide, placed about 23 meters away from that grapefruit. Jupiter would be the size of an orange, 120 meters away. The outermost planet, Neptune, would be nearly 800 meters, almost 1 kilometer, away from that grapefruit. And here is the truly terrifying part. Between that grapefruit representing the Sun and that marble representing Neptune, 800 meters away, there is literally nothing, just empty space. Aside from a few rocks and gas balls, a void stretching for kilometers. That is the solar system, a collection of lonely islands, isolated from each other, drifting in the dark. In this model, if you wanted to go to the next star, our neighbor Proxima Centauri, how far would you have to walk? If you were in New York City, standing in front of your door holding that grapefruit. The next star would be another grapefruit in Japan. the thousands of kilometers of ocean in between, are completely empty. And everything we have measured so far, the Earth, the Sun, the billions of kilometers of empty space, all of it, is just an invisible dot inside a single galaxy, the Milky Way. Place a single grain of rice in the middle of an American football field and call that grain the solar system. The Milky Way is not that stadium. The Milky Way is the entire city that stadium is in. The Milky Way is 100,000 light years across. So, our entire existence, all our signals, don't even cover 0.1% of our own galaxy. We measured the Earth and it vanished next to the Sun. We measured the solar system and it became invisible inside the Milky Way. At every step, the previous giant was erased by the next scale. So, is this the end of the scale? No, because just beyond the borders of the Milky Way, waiting in the darkness, is another structure that dwarfs the galaxy we thought was a giant. And that structure, right this second, is hurtling straight toward us at incredible speed. And this giant has a name. Andromeda. By every standard modern astronomy can measure, it is a structure larger, more populous, and hungrier than the place we call home. So far, we have measured the Earth, the Sun, and the void in between. They were all massive on a human scale. But they vanished on the next level up. Now, we must go even further. Because the Milky Way, no matter how large, is not alone. Its neighbor makes our galaxy look like a modest town. And right now, as we speak, it is busy closing that terrifying gap between us. This is the next and more disturbing level of cosmic scale. On autumn nights, if you look up at the sky in the northern hemisphere, you can see a faint blurry patch in the constellation of Andromeda. This is the most distant object visible to the naked eye. For centuries, astronomers simply called it a nebula, a gas cloud inside our galaxy, because our logic whispered that the universe consisted only of the Milky Way. But in the 1920s, when Edwin Hubble resolved individual stars within that patch, humanity experienced one of the greatest perspective shocks in history. That patch was not a cloud. That patch was an island universe, separate from us. The faint light you see when you look at that patch is actually the combined glow of about 1 trillion stars. A trillion, not a billion. The Milky Way galaxy contains an optimistic estimate of 200 to 400 billion stars. Andromeda has at least twice, and perhaps 5 times, that number. Even if you multiplied every star in our galaxy, every planet, every possible life form, you couldn't approach the population of our neighbor. That tiny, blurry patch contains more suns than our entire existence. The physical dimensions of this giant are equally overwhelming. While the Milky Way's disk is about 100,000 light-years across, Andromeda's disk spans 220,000 light-years. If we could place the two galaxies side by side, Andromeda would eclipse us like a beach ball eclipsing a tennis ball. This doesn't just mean being bigger, it means being in a completely different weight class. But the truly terrifying aspect of this giant is not where it is, but what it's doing. Andromeda isn't randomly drifting in space relative to us. Unlike all the other galaxies that are moving away from us with the expansion of the universe, it is approaching us. The blue shift in its light proves this definitively. Right now, every second you read this sentence, the distance between Andromeda and the Milky Way decreases by 110 kilometers. That's about 400,000 kilometers per hour. This speed is far greater than that of any human-made vehicle. Every year, Andromeda gets about 3.5 billion kilometers closer to us. That's equivalent to erasing the distance between the Sun and Uranus every single year. The two galaxies are locked in a mutual gravitational embrace, engaged in a dance that will last for billions of years. And the end of this dance, Wyalchi, is an absolute merger. In about 4 to 5 billion years, the sky will become unrecognizable, and these two giant structures will merge. But for now, what separates us is that terrifying distance, 2.5 million light-years. Since we heard this number, our brain has processed it as just data. But Gints, we must turn this data into a physical reality. Light is the speed limit of the universe. It travels at 300,000 kilometers per second. And even at this speed, a photon leaving Andromeda takes 2.5 million years to reach us. The light hitting your eyes when you look at Andromeda tonight, left when modern humans, Homo sapiens, did not yet exist on Earth. Our ancestors had not yet learned to control fire. When that light began its journey, nothing we call human history existed. Our entire existence fits into a tiny fraction of that light's travel time. If you convert this distance to kilometers, the number you get is 14.7 quadrillion kilometers, a 15-digit monster. This is not a distance the human mind can comprehend. It is an abstraction we can only accept mathematically. More importantly, this 14.7 quadrillion kilometer journey is covered in almost perfect nothingness. In intergalactic space, there is an average of just 1 atom per cubic meter. In the room where you are breathing right now, there are billions of molecules per cubic centimeter. In that void, in an area the size of a bathtub, there is only a single atom. This is emptier than the most advanced vacuums created in labs on Earth. No fuel, no stops, no safe harbor, just a dark, cold, and silent abyss stretching for 2.5 million light-years. Now let's look at the picture we have. On one side, a giant galaxy with trillions of stars. On the other, our modest home. And in the middle, a void that takes longer than human history for even light to cross. We've measured everything. We've mapped everything. The numbers are clear. The laws of physics are certain. But now we wonder. We even worry. Can we cross this distance with the rockets we have? The fastest vehicles we've built? Or the wildest technologies we can imagine? Is it possible to go to that neighboring galaxy? Or has the universe built an invisible cage for biological life forms? So, what does the real data say? When we take our calculators and divide humanity's greatest speeds by this distance, the result is not just a challenge. It's a devastating verdict on the fate of our species. Because the price of reaching that other shore is far heavier than we thought. And at that exact moment, the calculators fell silent. The theories on paper shattered when they collided with real data coming from the depths of space. Because the universe was not obeying the speed limits we had set. And at that exact moment, the calculators fell silent. The theories on paper shattered when they collided with real data coming from the depths of space. Because the universe was not obeying the speed limits we had set. It was not following the development scenarios we had written. When the most powerful telescope in human history, the James Webb, was launched into space, scientists expected to see baby galaxies, small, scattered, faint points of light. But when Webb opened its eyes, it didn't find babies. It found cosmic monsters. The first shock was named JADES-G-S-Z14-0. This name might sound like a complex code to you. But for the world of astronomy, this code is a synonym for the word impossible, because this galaxy was there just 290 million years after the Big Bang, a period when the universe was thought to be in its infancy, a time when even the first stars were just beginning to shine. This galaxy stood before us as a fully formed structure. According to the standard cosmological model, galaxies in such an early period of the universe should have been small. Gas clouds should not have collapsed enough. Stars should not have accumulated enough. But the Jade's galaxy ignored all these rules. Its diameter exceeded 1,600 light-years. It hosted hundreds of millions of solar masses in stars. And most importantly, it was incredibly bright. So bright that the star formation rate required to produce this luminosity was far beyond theoretical limits. The existence of this galaxy was like finding a child in a kindergarten class, suddenly teaching a university-level physics course. It shouldn't have been there. It didn't fit the timeline. The question of how the universe built such a large and bright structure in such a short time threw all simulations into the trash, because it takes time for gravity to gather gas and turn it into stars. It takes hundreds of millions of years. But this galaxy had finished the job in half that time and had started shining like a giant lighthouse. But Jade's was not alone. As Webb looked deeper, it encountered even bigger anomalies. The second shock came with the discovery of 6 giant galaxies, nicknamed the Universe Breakers. These galaxies were detected in a time frame about 500 to 700 million years after the Big Bang, and their sizes were, in the truest sense of the word, was mind-boggling. Some of these galaxies were as massive as our own Milky Way galaxy. It took the Milky Way billions of years to reach its current state. It required countless mergers, countless star formation cycles, and a 13 billion year evolution. These breakers, however, had reached the same mass in a period equivalent to 3% of the universe's age. Their masses ranged from 10 billion to 100 billion solar masses. These numbers meant that a significant portion of the total matter in that era had already been converted into stars. This situation raised the efficiency problem in cosmology. Normally, galaxies convert only a small fraction of their gas into stars. The process is inefficient. But these 6 galaxies seem to have converted every gram of gas they had into stars with nearly 100% efficiency. This was not physically possible. When scientists first saw this data, they said, there must be a mistake. But they checked again and again. They confirmed the distances with spectroscopy. There was no mistake. The galaxies were there. They were massive. And they were laughing in the face of our theories. The shockwave didn't end there. The third blow came from supermassive black holes. These monsters at the centers of galaxies were thought to grow slowly, over billions of years. But Webb found black holes of 10 million solar masses just 400 to 500 million years after the Big Bang. It even detected a black hole shining at the dawn of the universe. In the center of the galaxy, GN-11, the existence of this black hole raised the seed problem. There is a speed limit called the Eddington limit. A black hole cannot swallow matter above a certain rate to reach this mass, because the radiation emitted during swallowing starts to push back the incoming matter. But these early black holes seem to have violated this limit. Or, a more frightening possibility, they were born as heavy seeds. That is, not from the collapse of stars, but from the direct collapse of giant gas clouds into themselves. They had existed as monsters from birth. This was like seeing the face of an old man in a baby's photograph at 10 million solar masses, 400 million years. These two numbers could not come together. But they were. And finally, the fourth, and perhaps most jarring discovery: dead galaxies. The early universe was supposed to be a period of chaos, collisions, and frantic star formation. But Webb found a quenched galaxy, one that had completely stopped producing stars, just 700 million years after the Big Bang. Its name is JADES-G-S-Z7-01-QU. This galaxy had lived, rapidly produced its stars, consumed its fuel, and died. And it did all this in a period equivalent to 5% of the universe's current age. For a galaxy to retire so quickly was unexpected. Normally, galaxies continue to produce stars for billions of years. But this structure had flared up and died out like a cosmic firework. Or such a rapid death proved that the feedback mechanisms within the galaxy, namely the power of supernovae or black holes to expel gas, were much more violent than we thought. All these discoveries showed that the period we called the Dark Ages of the universe was not dark at all. On the contrary, it was filled with blinding speed and violence. Now we have old theories lying like a pile of rubble. And these massive, unexplained facts before us: the brightness of jades, the mass of the breakers, the impossible size of the first black holes, and the silence of the dead galaxies. They all scream the same thing. The beginning of the universe was very different from what we imagined. But the real question is, if the universe can build structures so fast, so efficiently, and so large, what does this mean for our future? And if the beginning was so violent, what will our end be like? And more importantly, where exactly are we in this cosmic roller coaster? Because, in the shadow of these massive structures, our place is far more uncertain. And this uncertainty is not just a lostness about our cosmic address. And this uncertainty is not just a lostness about our cosmic address. It's causing a terrifying distortion in our perception of time. Because, as the Webb telescope pulled back the dark curtain of space, it revealed not only the large, but also the impossibly orderly. The baby universe was supposed to be a chaotic, messy, and shapeless soup. Physical simulations had told us this. But when Webb's data hit the screens, scientists were met not with chaos, but with a cosmic ballet. See, the name of this new shock was mature disk galaxies. Structures like Rebels 25 were there, just 700 million years after the Big Bang. And they had something they theoretically shouldn't have: a perfect rotation. According to standard cosmology, the early universe is a violent place. Gas clouds collide, gravity is unstable, and galaxies are expected to look like train wrecks, formless, lopsided, messy clumps, because it takes billions of years of settling down for orderly, spiral-armed disks that rotate calmly around themselves, faulty like the Milky Way, to form. The chaos is expected to end, and gravity is expected to bring the system into equilibrium. But Rebels 25 threw this scenario out the window. In a time equivalent to 5% of the universe's age, it had formed a disk structure as cool-headed and stable as today's Milky Way. Its rotation speed reached hundreds of kilometers per second. The gas movements were as orderly as in billion-year-old galaxies. This was like finding a working jet engine. Built in the Stone Age, it shouldn't have been there. Because, for angular momentum to evolve into such an orderly structure in such a short time is contrary to our known fluid dynamics. This galaxy seemed to have skipped its adolescent and youth phases entirely and gone straight to adulthood. This discovery showed that galaxies mature much faster than we thought, and that order emerges from chaos 10 times faster than we predicted. The simulations were wrong. The universe was a much better artist at managing chaos than we were. But Webb didn't just find order. It also found monsters that should have been invisible. A series of discoveries called little red dots created a real panic in the astronomy world. These objects, which at first glance appeared as just faint red smudges in the depths of the sky, revealed a terrifying truth when subjected to spectroscopic analysis. These were not ordinary galaxies. These were super-dense structures harboring black holes impossibly massive for their size. The numbers were mind-boggling. The radius of these dots was only about 100 light-years. That's 1,000 times smaller than our Milky Way galaxy. But the supermassive black holes they harbored weighed between 10 million and 100 million solar masses. In a normal galaxy, the central black hole makes up only 0.1% of the galaxy's total stellar mass. This is a universal ratio. But in these little red dots, the mass of the black hole was nearly equal to the stellar mass of the galaxy. This was like a person carrying a stone in their stomach equal to their own body weight. It seemed physically unsustainable. How could a black hole become so dominant without swallowing or disrupting its host galaxy? And more importantly, there weren't just one or two of these objects. Webb found hundreds of them in the early universe. They were 100 times more common than expected. Theorists were in shock, because this discovery refuted the idea that black holes and galaxies grow together. It seemed that black holes form first, grow first, and galaxies form around them later. This was a cosmic answer to the chicken or the egg question, and the answer was terrifying. The monster came first, and finally, a chemical impossibility entered the scene. When Webb looked into the first 600 million years of the universe, it found elements that shouldn't have been there: carbon, oxygen, and dust. There is a fundamental rule in cosmology. The Big Bang produced only hydrogen and helium. All other elements, the metals, etc., are cooked in the cores of stars, and when those stars die, they are scattered into space by supernovae. For the building blocks of life like carbon and oxygen, stars need to be born, live, and die. This is a cycle, and it takes time. But Webb detected intense amounts of nitrogen, carbon, and dust in galaxies like GN-ZD11. How could space be filled with the ashes of dead stars when the universe was still in its infancy? When had enough stars lived and died to produce these elements? The data pointed to the existence of legendary giant stars, called population 3 stars, composed only of hydrogen and helium, in the early universe. But here, the amount of this dust showed that these stars flared up and died out much faster than we predicted. And their life cycles were not millions, but perhaps only hundreds of thousands of years long. The cosmic furnaces had worked much hotter and faster than our models allowed. While we were saying impossible, the universe had already begun building the blocks of life. Every one of these discoveries, the size of jades, the mass of the breakers, the order of mature disks, the density of the red dots, and the early dust, all scream one truth. The universe's calendar is broken. The history book we wrote does not match reality. Yet the universe woke up faster than we thought. It grew faster and aged faster. These discoveries are not just numerical errors. They are cracks in the fundamental narrative of our existence. But the fascinating thing in science is not just what we find, but how we find it. Because the Webb telescope isn't just looking into space to see these impossible structures. It's bending the fabric of time, the physics of light, and the expansion of the universe, with the most complex engineering marvel the human mind has ever designed. Without understanding how these giant mirrors capture those faint, dying heat signals from 13 billion years away, we cannot fully grasp the terror of what they see. So, how do these golden honeycombs actually work? What is the miraculous mechanism that turns that phantom light from billions of years ago, in that dark and cold void, into an image? Because this machine is not just a telescope. Because this machine is not just a telescope. It is the most sophisticated time machine humanity has ever built to bend the laws of physics in its favor and rewind time. Now, it's time to descend into the heart of that machine, to its cold and silent core. Because, without understanding how this technology works, how it captures those faint particles of light from billions of years away and reveals the deepest secrets of the universe, we cannot fully appreciate the value of what we see. The success of the James Webb Space Telescope is not a coincidence. It is the result of a series of critical mechanisms, each an engineering marvel, working in perfect harmony. The first and most fundamental mechanism is Webb's eye, its giant golden mirrors. You can think of a telescope as a giant light bucket. The wider its mouth, the more raindrops, or photons, you can collect. The Hubble Space Telescope showed us the wonders of the universe for years. But its primary mirror was 2.4 meters in diameter. While this was a respectable bucket in the cosmic ocean, it's like a teacup next to Webb's. Because, Webb's primary mirror is a full 6.5 meters in diameter. This massive surface area means about 6.25 times more light collecting power than Hubble. But launching a mirror of this size into space in one piece is impossible. No rocket has a payload bay wide enough to hold a 6.5 meter glass disc. So, engineers solved this problem by taking inspiration from nature, from bees' honeycombs. Webb's mirror is not a single piece. It is composed of 18 separate hexagonal segments, each 1.32 meters wide. These segments were folded up like origami inside the rocket during launch, and millions of kilometers away. In space, they unfolded with micrometric precision to become a single giant mirror. The material of these mirrors is not ordinary glass. Because glass is heavy, and it expands and contracts with temperature changes in space, losing its shape. Instead, beryllium was used. Beryllium is 6 times stiffer than steel, yet 1/3 lighter than aluminum. But more importantly, beryllium retains its shape at a microscopic level, even at cryogenic temperatures, near absolute zero. Each segment is coated with a layer of gold, 1,000 times thinner than a human hair. Because gold is one of the most efficient metals in the universe for reflecting infrared light. This thin gold layer transmits those faint heat signals from the universe's first stars to the sensors with 99% efficiency. The second critical mechanism is Webb's sunglasses. Hidden behind this giant golden eye, its massive heat shield. Webb is designed to see the coldest or faintest objects in the universe. These objects don't emit visible light. They emit faint signals that have been redshifted by billions of years of cosmic expansion, turning into heat energy. To capture these signals, the telescope itself must be absolutely cold. If the telescope heats up, its own heat will blind the sensors. It's like trying to see stars by looking at the sun during the day. So, to block the heat from the sun, Earth, and Moon. Webb carries a 5-layer sun shield the size of a tennis court. This shield is made of a heat-resistant plastic film called Captain. Each layer is colder than the one before it, and the vacuum between them allows heat to radiate away into space. The sun-facing side of the shield heats up to about 85 degrees Celsius. This is near the boiling point of water. But on the other side of the shield, the dark side where the mirrors and sensors are, the temperature drops to minus 233 degrees Celsius. This is only 40 degrees Celsius above absolute zero. This temperature difference is about 300 degrees. On one side, water boils, siyasat. On the other, nitrogen freezes. Each layer of the shield is so thin. It's the thickness of a human hair. But these 5 layers reduce the 200,000 watts of heat energy from the sun to just 0.02 watts on the back side. This is like reducing the heat of a nuclear explosion to the heat of a match. Because, without this passive cooling system, Webb's sensitive infrared eyes would be blinded in seconds. The telescope would be deafened by the noise of its own temperature and could never hear those billion-year-old signals. The third, more, and perhaps least known but most vital mechanism is Webb's location, Lagrange, point 2. The Hubble telescope orbits the Earth at an altitude of about 540 kilometers. This is close, it's accessible. But it's problematic. Because the Earth blocking the Sun every 90 minutes causes temperature fluctuations and limits observation time. Also, the Earth's own heat and radiation from its atmosphere make infrared observations difficult. Webb, however, parked far from home, 1.5 million kilometers away, at the L2 point. This distance is about 4 times the distance from the Earth to the Moon. The L2 point is a special region of space where the gravitational forces of the Sun and Earth balance out. Here an object can stay aligned with the Earth and orbit the Sun at the same speed as the Earth. This location offers Webb a unique advantage. The Sun, Earth, Shoss and Moon are always on the same side. This allows the massive heat shield to always face these 3 heat sources, while the sensitive side of the telescope can peer into the darkness of infinite space. Webb experiences no day-night cycle. It's not exposed to temperature fluctuations. It can perform 24/7, continuous, uninterrupted observations. While Hubble spends a significant portion of its time waiting, entering and exiting Earth's shadow, Webb collects data non-stop. This location gives it not only thermal stability, but also operational efficiency. But this distance comes at a price. If it malfunctions, you can't go and fix it like Hubble. Sending a team of astronauts there is impossible with our current technology. So, Webb either had to work flawlessly, or it would become a $10 billion piece of space junk. The fourth mechanism is the brain that turns light into data, the ANIRCam and MIRI instruments. These are not ordinary digital cameras, and due to the expansion of the universe, the light from the oldest stars and galaxies has shifted from the visible spectrum to the infrared colors our eyes see, to the infrared spectrum, which is heat. To solve for this redshift phenomenon, Webb's sensors are designed to detect wavelengths much longer than the human eye can see. NIRCam, the near-infrared camera, sees wavelengths between 0.6 and 5 microns. This is ideal for taking baby pictures of the universe. But the MIRI instrument goes down to longer wavelengths, between 5 and 28 microns. These wavelengths are necessary to look inside cosmic dust clouds, to study planet-forming disks, and to read the chemical signature of the oldest galaxies. Passive cooling is not enough for MIRI to work. Even minus 233 degrees Celsius is too hot for it. MIRI is cooled down to minus 266 degrees Celsius, just 7 degrees Celsius above absolute zero, with a special mechanical cooler called a cryocooler. At this temperature, atoms almost come to a standstill. Electronic noise is completely silenced. And in this silence, MIRI becomes so sensitive that it could detect a candle flame on the moon. These four mechanisms, the foldable beryllium mirror, the 5-layer heat shield, the L2 orbit, and the cryogenic sensors, have come together to fundamentally change humanity's cosmic vision. But Webb's capabilities are not limited to looking at the past. This telescope is also being used to seek an answer to one of life's biggest questions in the future. Because there is another method Webb uses to detect these things. And this method is perhaps the most exciting of all. It's called spectroscopy. While the fascinating color photos taken by the James Webb Telescope are great for public relations, for scientists, the real treasure is hidden in the invisible data behind these photos. Because a photograph tells you that an object is there, but spectroscopy whispers to you what that object is made of, how hot it is, how fast it's moving, and whether you could breathe in its atmosphere. So, Webb is not just a photographer of the universe, it's also its most skilled chemist. To understand how this system works, imagine a supermarket checkout. When you pass a product through the checkout, the laser reader scans that complex set of black lines, the barcode, and instantly, the screen displays what the product is, its price, and its brand. Every element in the universe, hydrogen, carbon, oxygen, water, methane, has a unique and inimitable barcode, just like those products. And that barcode, is light. Webb's NIRSpec instrument takes that faint light from billions of years away and separates it into its components, like a prism. When the light is spread into a spectrum, a rainbow-like display of colors appears. But within this rainbow, there are thin black lines where specific colors are missing. These are the cosmic barcodes, because as light passes through a planet's atmosphere or a galaxy's gas cloud, the atoms there absorb specific wavelengths. So by analyzing these missing parts, Webb can say with absolute certainty whether there is water vapor in the atmosphere of a planet 1,000 light-years away, or whether carbon was being cooked in a galaxy 13 billion years ago. Hubble could also do spectroscopy. But Webb's capacity, compared to Hubble's acids, is like the difference between a blurry photocopy and a 4K resolution digital scan. Because Webb can take the spectrum of 100 different objects at the same time. This means looking at a tiny square of the sky and solving the chemistry of hundreds of galaxies there, all at once. This increase in efficiency is a revolution in astronomy. But making such a precise measurement brings a huge logistical problem. Space is full of stars. When you want to focus the telescope on a galaxy, the light from other bright stars in the background or dust in the foreground can drown out the faint signal you want to study. This is like trying to hear a single person's whisper on the opposite side of a crowded, noisy stadium. Everyone else needs to be quiet. This is where Webb's most surprising, most mechanical, and most science fiction aspect comes into play: the micro-shutter array. This technology is the first programmable masking system ever sent to space. Inside the NER spec instrument, there are 4 silicon wafers the size of a postage stamp, and on these wafers are a full 248,000 tiny windows, solmikas, or shutters. Each shutter is about 100 by 200 microns in size. This is equal to the width of a few human hairs. When Webb looks at a specific region of the sky, scientists choose which stars or galaxies' light they want to let in and which they want to block. A magnetic arm passes over these thousands of tiny windows, leaving only the desired windows open and tightly closing the others. This way, Webb physically blocks the noise in that region. The light from unwanted stars hits the closed windows and disappears, while the light from the targeted ancient galaxy filters through the open window and reaches the sensor. Without this mechanism, it would be impossible for Webb to take those deep field images and make those precise chemical analyses. In older telescopes, this process required drilling holes in metal plates and placing them inside the telescope. Is Webb afraid? However, does this millions of kilometers from Earth, with a magnetic touch, assigns in seconds. Despite all these optical and mechanical wonders, the giant mirrors, the precise shutters, the cold sensors, would be useless if the telescope vibrated. Anyone who has done long exposure photography knows how critical it is for the camera to remain stable. Webb sometimes has to look at the same point for hours, even days, to image the faintest objects in the universe. The system that provides this stability is the fine guidance sensor. Webb's posture in space is so precise, that the metaphors used to describe this precision push the limits of the mind. The telescope's pointing ability has a precision of 7 milliarcseconds. To put this in terrestrial terms, this is like standing in New York City and pointing a laser at a coin in Washington, D.C., 500 kilometers away, and holding the laser on that coin for hours without it shaking. This incredible stability is achieved by the telescope checking stars 16 times per second and correcting its position at a microscopic level. Because even in the vacuum of space, the pressure of the solar wind, the vibration of the internal coolers, or the movement of the antenna can shake the telescope. The sensor instantly detects these tremors and moves the mirrors or the spacecraft in the opposite direction to freeze the image. This way, those tired photons that have traveled for 13.4 billion years fall on the exact right pixel of the sensor and turn into a sharp history lesson instead of a blurry smudge. This engineering symphony, the foldable beryllium mirrors, the 5-layer heat-destroying shield, the spectrographs that turn light into a barcode, the 250,000 microshutters that block unwanted light, and the targeting system that can hit a coin in Washington, all came together for one purpose: to push humanity's boundaries to places it cannot physically go. We built this machine, put it on top of a rocket, and launched it 1.5 million kilometers from Earth into a darkness of no return. And finally, when that golden eye opened, we were generously rewarded. However, what Webb showed us was not just technical achievements or beautiful wallpapers. When this machine lifted the veil of the universe, what we found there were not just new galaxies. What we found there was a difficult-to-face, jarring truth about how fragile, how small, and at the same time, how rare our existence is. Because, no matter how perfect the technology, the landscape it reveals does not change. And now, it's time to look at the big picture that all these mechanisms, all these mirrors and sensors have shown us. The most terrifying part of the story. The climax. Get ready, because the scale now transcends even galaxies, and now comes the real miracle. What you have heard so far, early galaxies, giant black holes, mature disks, was just a warm-up. The Webb telescope didn't just crack open the curtain of the universe. It ripped that curtain down and threw it away. And out of that tear poured the biggest, most distant, and most shocking secrets of our cosmic history, pushing the limits of the human mind. This is not just science. This is an existential earthquake. Prepare yourselves, because the scale now transcends even galaxies. We are now going to the extreme edge of time, space, and matter, to the edge of the cosmic abyss, and now comes the real miracle. What you have heard so far, early galaxies, giant black holes, mature disks, was just a warm-up. The Webb telescope didn't just crack open the curtain of the universe. It ripped that curtain down and threw it away. And out of that tear poured the biggest, most distant, and most shocking secrets of our cosmic history, pushing the limits of the human mind. This is not just science. This is an existential earthquake. Prepare yourselves, because the scale now transcends even galaxies. We are now going to the extreme edge of time, space, and matter, to the edge of the cosmic abyss. The name of the first epic moment is Earendel. This name means morning star. This is not an ordinary discovery. This is the most distant, the oldest, and the loneliest star humanity has ever seen. A single star, not a galaxy, not a cluster, just one single sun, shining from 12.9 billion years ago. It was there when the universe was only 900 million years old. Normally, seeing a single star from this distance is physically impossible. Even the most powerful telescopes can only see the combined light of billions of stars at this distance as a blurry patch. But the universe helped Webb. A cosmic magnifying glass called gravitational lensing magnified Earendel's light a full 4,000 times. This star is at least 50, perhaps even 100 times more massive than our Sun. Its surface temperature exceeds 20,000 degrees Celsius. A massive, furious, blue nuclear reactor. Millions of times brighter than the brightest stars in the Milky Way. But the truly shocking part is its solitude. It is a single, shining jewel within a galaxy stretched like a bow by the bending of space-time, called the Sunrise Arc. This discovery was a holy grail moment in astronomy, because, for the first time in history, we came face to face with an individual actor who lived at the dawn of the universe. When that light set out, the Earth did not exist. The Sun did not exist. The Milky Way was just a cloud of gas, and after drifting through the void for 12.9 billion years. It struck Webb's golden mirror. Earendel is not just a star. It is a ghost from the youth of the universe. And what it whispers to us is this: in the beginning, there were giants, far larger than you thought. This discovery required us to rewrite all theories about the first stars. Because the existence of such a massive star so early proved that the first stellar populations were far more diverse and violent than we had imagined, if than the Sun. Made only of hydrogen and helium, incredibly hot and short-lived. And the life cycles of these monsters lasted not for millions of years, but perhaps only a few 100,000. The cosmic furnaces had worked much hotter, much faster, and much more efficiently than our models allowed. The universe had already begun to build the blocks of life, while we were still saying, impossible. This was not just an astronomical discovery, it was a clue to the origin of biology. Could life itself have emerged much earlier in the universe than we thought? But the only order Webb found was not at the chemical level. One of the biggest shocks came at the structural level. The baby universe was supposed to be a chaotic, messy soup hole full of collisions. Physical simulations had told us this again and again. The first galaxies were expected to be lopsided. Irregular clumps, nodes, like train wrecks. Because it should take billions of years of settling and calming down for elegant, orderly disk structures with spiral arms, like our Milky Way, to form, rotating peacefully around themselves. The chaos had to end. Gravity had to bring the system to equilibrium. But Webb threw this scenario out the window as well. It presented us with structures like Rebels 25. This galaxy was there, just 700 million years after the Big Bang. And it had something it theoretically shouldn't have. A perfect, stable and orderly disk structure with a calm rotation ongoing in this disk. The rotation speed reached hundreds of kilometers per second. The gas movements were as orderly as in old Yamasatrich, mature galaxies billions of years old. This was like finding a working Swiss watch in the Stone Age. It should not have been there. Because, for angular momentum to evolve into such an orderly structure in such a short time, in such a violent environment, was completely contrary to our known fluid dynamics and gravitational physics. This galaxy seemed to have skipped the adolescent and youth stages of evolution and gone straight to adulthood. This discovery proved that galaxies mature 10 times faster than we thought. Order was born out of chaos much more quickly and efficiently than we had predicted. The simulations were wrong. The universe was a much more masterful artist at managing chaos and creating order than we had ever assumed. And then, among all these massive structures and rapid processes, Webb made a discovery that forced us to ask perhaps the most fundamental, most personal question of all. Are we alone? To answer this question, one needs to study the atmospheres of potentially habitable planets. And Webb was a game changer in this regard as well. The target was an exoplanet called K2-18b, a super-Earth about 8.6 times more massive than our planet. It orbits in its star's habitable zone, that sweet spot where water can remain liquid. Hubble had previously detected water vapor in this planet's atmosphere. But Webb went deeper, and what it found created a wave of excitement in the scientific community. Webb found evidence in K2-18b's atmosphere not only of water vapor and methane, but also of the possible presence of a molecule called dimethyl sulfide, or DMS. Why is this so important? Because, on Earth, DMS is largely produced only by living organisms, especially by phytoplankton in the oceans. This was a biosignature, a potential chemical fingerprint of life. This does not mean there is life on K2-18. B, it absolutely does not. But, for the first time in history, we had found a clue to a molecule on another world, one strongly associated with life on Earth. This discovery took exoplanet research to a new level, and we are no longer just asking, is there a planet there? We are now asking, what's in that planet's atmosphere? And, is there a trace of life in that atmosphere? Webb gave us the power to ask these questions and to search for their answers. In the vastness of the universe, we had heard a potential whisper of life, and that whisper, amidst all the noise, was perhaps the most meaningful of all. All these discoveries, the lonely light of Earendel, the impossible brightness of Jades, the massive bulk of the breakers, the gluttonous black holes, the sudden cosmic deaths, the early arrival of heavy elements, the unexpected order, and the potential whispers of life, they all point to one thing. The beginning of the universe was completely different from our calm, shatters, slow, and orderly models. It was a place full of speed, violence, efficiency, and unexpected surprises. All the history books we've written, the simulations, and the theories must be revised in light of this new reality. We are experiencing a paradigm shift. We are witnessing the golden age of cosmology. Every new image from Webb invalidates a textbook and raises dozens of new questions. The universe is not giving us its secrets slowly, but like a flood, like a shockwave. But now it is time to step back for a moment from this dizzying speed, from this bombardment of epic discoveries. Time to stop, take a breath, and think about what all this means for us, for the curious creatures on this small planet. Because these numbers, these distances, and these theories are not just abstract scientific data. They hold a mirror to our deepest existential questions. What is our place in this massive, violent, and seemingly incomprehensible universe? Is the feeling of smallness we feel in the face of all this greatness a curse or a blessing? And most importantly, what will we do with this knowledge? Because solving the secrets of the universe is one thing, but finding our own meaning within those secrets, that is a completely different journey. And now, it is time to begin that journey. Let us step away for a moment from this dizzying speed, from this bombardment of epic discoveries. Let's stop and take a breath, and let's think about what all this means for us, for the curious creatures on this small, pale blue dot. That because, Ositadins, these numbers, these quadrillions of kilometers, these billions of years, are not just abstract scientific data. They hold a mirror to our deepest existential questions. What exactly is our place in this massive, violent, and at first glance, incomprehensible universe? Is that overwhelming sense of smallness that awakens within us in the face of all this greatness a curse, or is it actually a blessing? And most importantly, what will we do with this knowledge? Because solving the secrets of the universe is one thing, but finding our own meaning within those secrets, that is a completely different journey. The first and most fundamental confrontation is the tragicomic contrast of our dimensions. On one hand, there is a universe that grows ever larger with each new discovery, its boundaries pushing the limits of our minds. The diameter of the observable universe is 93 billion light-years. That's a number of kilometers you have to add 22 zeros to. It contains at least 2 trillion galaxies, and each galaxy contains hundreds of billions of stars. Neighbors like Andromeda are so massive they dwarf our entire existence. Black holes are so dense they can swallow stars in a single gulp. This is an overwhelming greatness. On the other hand, there's us, with our average height of 1.7 meters, our 3-pound brain, and our lifespan of about 80 years. Physically, on a cosmic scale, we are nothing. If the universe is an ocean, we are not even a single water molecule in that ocean. This is a tragic fact that is hard to accept. Our biology has made us prisoners of this thin atmosphere, this delicate temperature range, and this gentle gravity. We will never go to Andromeda. We will never touch the surface of Earendel. Even with our fastest rockets, it would take tens of thousands of years to reach the nearest star. We are physically chained to this planet, to this fragile body. 99.99% of the universe is filled with conditions hostile enough to kill us instantly. This can create a deep sense of sadness and helplessness. We are the most insignificant, most fragile actors on this grand stage. But there is that magic word. But right in the midst of this physical impotence, the greatest miracle of the universe blossoms. That 1.3 kilogram jelly-like organ, that brain running on as much energy as a dim 20-watt light bulb, can contain the 93 billion light-year universe within itself. You may be physically trapped in this room, in this city. But with your mind, you can go to the moment of the Big Bang right now. You can solve the mathematics of black holes, analyze the chemistry of stars, and map galaxies you will never set foot on. It was not the strongest, the biggest, the most violent. It was the weakest that understood. Stars are massive nuclear reactors, but they do not know themselves. Galaxies collide, but they are not aware of what they are doing. You, however, that fragile being who can get sick from a virus, who can fall and break a bone, are the only thing that knows what all those massive objects are. The Webb telescope is the very embodiment of this mental power. It is the extension of our minds that we send to places our fragile bodies cannot go. Therefore, your physical smallness should not drive you to despair. Because to be able to comprehend your own smallness is a task only a colossal consciousness can perform. You, too, from where you sit, can imagine billions of light years away. While your body is a prisoner of gravity, your thoughts exceed the speed of light. This is your cosmic superpower. The universe may be made of matter and energy. But meaning is an element that exists only in your mind, and you are a factory that produces that rare element. Our second confrontation is the ruthless contrast between the eternity of time and our fleeting existence. On one hand, there is a universe with a 13.8 billion year past and a future stretching for trillions of years. Time is measured in geological eras. The lifetimes of stars, the rotations of galaxies. On this timeline, human history is shorter than the blink of an eye. All our wars, our empires, our inventions, our joys and sorrows do not even amount to 1,000th of a second on that vast cosmic calendar. This is a tragic fact about the transience of our existence. The ruthless laws of thermodynamics tell us this. Entropy increases. The universe, in billions, trillions of years, will reach a state called heat death. Stars will stop being born, black holes will evaporate, and what will remain is an infinite nothingness, where only cold, dead photons float. Our existence, our civilization, the Webb telescope, the pyramids, the poems we write, and the equations we solve will all break down into their atoms and be forgotten. We are nothing but a cosmic spark, flashing for a moment in this dark ocean and then fading. This knowledge opens the door to nihilism. The question, if everything will be destroyed, why do we even try? Echoes in the dark corners of the mind. But, there's that word again. But, right on the edge of this abyss, an immense beauty and resistance blooms. Because the existence of an end does not devalue the present moment. On the contrary, it makes it unique. The fact that the universe will one day die does not change the fact that it is alive right now. More importantly, the fact that the universe will remain in darkness for trillions of years makes it all the more precious that right now, in this brief sliver of time, it possesses a self-aware consciousness, which is us. We are the temporary memory of the universe. Thanks to our existence, the universe has gone from being merely that which exists to that which is known. Our capture of those photons with the Webb telescope, our mapping of those galaxies, is the universe's way of recording its own history. If we did not exist, those massive explosions, those colourful nebulae, those silent collisions, would have passed by unseen, unappreciated, uncomprehended. Even if everything will be forgotten one day, the fact that it is known now adds meaning to existence. Even after the sound fades, the echo hangs in the air, but you too are an active cell of this cosmic memory. Every piece of knowledge you learn, every sense of wonder you feel, is a contribution to the universe's process of understanding itself. When you are gone, what you knew may also vanish. But the fact that you knew is a lived and irreversible truth. In the history of the universe, there is a period where it can be said, once someone looked at the stars and understood what they saw, and you are living proof of that era, of that golden age. So, knowing that the end will come should not lead you to despair, but to appreciate the value of the moment, because this stage will not be set again. The third, and perhaps most personal confrontation, is the eternal battle between fear and curiosity. Is everything we've described, those massive voids, those destructive explosions, those unreachable distances, naturally creates fear as an instinct. Humans evolved to be terrified in the face of massive things they do not know and cannot control. The fact that Andromeda is coming towards us, that the sun will one day swallow us, the possibility that we are alone in the universe. These are realities that can keep us up at night, that can create existential crises. This fear is extremely human and tragic, because we need security, control, and to be at the center. But the universe gives us none of these. It constantly slaps us in the face with the fact that we are not safe, that we are not in control, and that we are not the center. This cosmic horror creates a Lovecraftian shudder. We feel as if we are on a tiny raft in the middle of the ocean, amidst giant waves. But, and this is perhaps the most beautiful but in the human spirit, there is a drive more dominant, more irrational, and more beautiful than fear, curiosity. Even if we are afraid, we keep looking. Even if we are terrified, we want to learn. When we launched Webb, weren't we afraid of what we would find? Weren't we worried that our theories would be shattered? That our loneliness would be confirmed? Of course we were. But our curiosity defeated our fear. This is the noblest part of being human. We are afraid of the dark, but we still enter that darkness with a flashlight in hand. Standing on the edge of a cliff makes our head spin, but we can't stop ourselves from looking down, because to know, despite the fear, is our reason for being. You too, as you read this text, are actually confronting your own fear. You are suppressing that primitive instinct that says hide and listening to that civilized voice that says show me. And this courage is what transforms us from being victims of the universe to its students. Fear paralyzes us. Curiosity moves us. We are that strange, that stubborn species that, despite being afraid, does not close its eyes, but instead builds giant golden mirrors to see better. And this stubbornness is our signature in the universe. But all these confrontations, all these contrasts, merge into one big question. And this stubbornness is our signature in the universe. Because therefore, all these confrontations and all these contrasts now lead to a deeper, more personal question. In light of all that we have learned, how do you feel about yourself? What emotions do the measurements and comparisons we've made throughout this journey evoke in your mind? This is not a simple question, because the answer defines our most fundamental relationship with the universe. And this answer probably oscillates between two opposite poles. One part of you says, how small I am, how insignificant, and you feel crushed under those massive numbers, those quadrillions of kilometers. You think you cannot make an impact even as much as a dust mote. This feeling is absolutely true. That emptiness you feel in your stomach, that dizziness, is a physical reaction to the truth, because feeling humility in the face of the universe's immensity is a sign of a healthy mind. It reminds us of our limits, our fragility, and our cosmic solitude. This is a tragic but necessary lesson that saves us from the ego trap. We are not the center of the story. We are just temporary passengers on a small planet. Facing this truth requires a certain maturity, and this smallness you feel is proof of that maturity. But another part of you feels a strange pride, an expansion, a sense of grandeur. I can know all of this, you say. My mind transcends these walls. I am the part of this grand story that is aware of it. This feeling is also absolutely true, because to be able to comprehend one's own smallness is a task only a colossal mind can perform. Only a vast consciousness can perceive its own absence and insignificance. The animals, planets, stars do not contemplate their own unimportance. But you can, and that makes you special. These two feelings can exist in the same heart, at the same time. In fact, they should, because we are at the very intersection of the concepts of large and small. We are both the most insignificant detail of the universe and its most valuable observer. This duality is the definition of being human. To feel both lost and at home at the same time is the greatest gift this journey has given you, and this duality manifests itself in another fundamental contrast: the chasm between our biological fragility and our mental power. Physically, we are extremely weak. We have a 1.3 kilogram brain made of flesh and nerves. This brain operates on about 20 watts of energy, the power of a dim light bulb. Our bodies die within minutes without a specific temperature range, a specific pressure, and a specific atmospheric mix. We have no natural defense against the freezing cold of space. It's deadly radiation. This is a tragic limitation. We were not designed to leave the incubator called Earth. Going to K218b, reaching Andromeda, approaching black holes. these are suicide for our biology. 99.99% of the universe has conditions that would kill us instantly. We are like houseplants on a cosmic scale. The moment we leave our pot, we are doomed to wither. Our physical strength is nothing against the violence of the universe. But here is the most powerful but. Within this biological weakness lies a power that transcends the laws of physics. That 1.3 kilogram jelly-like organ running on 20 watts can contain the entire universe. From where you sit, you can solve the mathematics of black holes, calculate the density of neutron stars, and map galaxies you can never visit. While your body is chained to Earth, with your mind, you can travel to the beginning of time, to the moment of the Big Bang. This is the universe's greatest paradox. The weakest understood the strongest. Stars are massive nuclear reactors. Why? But they do not know themselves. Black holes swallow galaxies, but they are unaware of what they are doing. You, however, that fragile being who can fall and break a bone, are the only thing that knows what all those massive objects are. The Webb telescope is the embodiment of this mental power. It is our extended mind, sent to places our fragile bodies cannot go. You have this power too. While your body is a prisoner of gravity, your thoughts exceed the speed of light. This is your cosmic superpower. Instead of grieving your physical impotence, you should take pride in the boundlessness of your mental capacity, because you are a rare factory that produces meaning. Now we know. At the beginning of our journey, we measured the size of the Earth and thought it was big. Then we looked at the sun, and the Earth disappeared. We looked at the solar system, and the sun disappeared. We looked at the Milky Way, and our system became invisible. We looked at Andromeda, and our galaxy shrank. And with Webb, we looked to the beginning of time, and everything collapsed into a single point. This journey of scale systematically demolished our ego. It showed us our physical limits, our biological cage, and our temporal transience. It taught us that we will never go to Andromeda, that we will never exceed the speed of light, and that we will never rule the entire universe. These limits are rigid, real, and insurmountable. But the same journey taught us something else, and that is, we have no cognitive limits. Although we are physically trapped, we can go beyond those walls with tools like Webb, languages like mathematics, and emotions like curiosity. We are like stars that cannot escape their own gravity, but can send their light everywhere. The journey is ending. The numbers, distances, theories, and paradoxes have fallen into place. Now, when you look at the sky, you will not just see bright dots. You will see the void between those dots, the history within that void, and your own place within that history. Andromeda is no longer just a smudge. It is your unreachable neighbor, your cosmic mirror. And now, it is time to melt all this data, all these emotions, and all this philosophy in one crucible, and arrive at the final word, the ultimate verdict. Because where science ends, meaning begins. And the meaning of this story is not hidden in the vastness of the universe, but in the courage of the eyes that can see that vastness, which is you. Today, we measured the limits of the universe, those massive distances, and our own physical reality. But there is one more possibility I haven't told you. One that will keep you up at night. What if this infinity is just the rendering limit of a piece of software? What if those unreachable galaxies and laws of physics are just lines of code? Today, we measured the mind-boggling dimensions of the universe and our physical limits. But there's something I didn't tell you. What if this three-dimensional reality we measured is just an illusion? What if this entire universe is a reflection of two-dimensional code written on a distant horizon? A hologram. On our next journey, we will question reality itself. Is the universe a hologram? Are you ready?